Without further ado, let me introduce you to Adam Kaplan.
Hi, everyone. I hope you all can hear me okay. Can I just get a quick check in the chat box? You can hear me? Yes. Okay, great. Today we're going to be doing a free HydroComp webinar. We are going to be using PropCad to recreate a propeller design from a drawing. The objective of this webinar is to demonstrate the basic propeller creation process within PropCad. Let me just pull up PropCad here so we can see the program. So we're first going to create a basic design, and then we're going to manually enter data into PropCad to modify the design. We will first use the PropCad builder to create the initial geometry of the propeller, as similar as we can to our desired design. And then we will, from the propeller drawing, we'll take the radial distributions of pitch, chord, skew, and thickness, modify those to get the propeller a little closer. And lastly, we'll look at the sections in the drawing. We'll try to identify those, and then we'll actually enter the offsets in to fully match the propeller from the drawing using the offsets. These type of section definitions are reusable between different designs, and you'll often find yourself having to modify these distributions and enter these section files. Before we get started, let me just say that at any time, feel free to ask questions using the text message field on the bottom right of any meeting. I will address these questions at the end of the presentation and open up the microphone for questions. Let's get started. First, let me review the PropCad interface. On the left side here, we have our major design characteristics such as diameter, reference pitch, the calculated blade area ratio, and the calculated skew angle. We can also optionally enter information about our design, which will be featured in the drawing. In the right side here, we have our 3D preview of our 3D geometry. The bottom tab here will bring up the 2D drawing. Let me just pull that up here so you can see that real quick. And then at the top, we have a navigation toolbar, the typical things such as the new file, open file, save file, and show offsets. And then we have the definitions that PropCad uses to define the propeller. We have the strength of materials definition, we have the sections definition, the hub definition, and the tip definition. So now let's look at our desired design. This is a drawing of a 5-bladed 250mm fixed pitch propeller known as the KP505. It was published in a study about performance of a Chryso container ship. We'll first identify our major characteristics, such as diameter, nominal pitch, blade area ratio, rake angle, and total skew angle, in order to quantify the overall blade shape. These are published in the drawing blocks themselves, and we'll use this as our starting point. We can see down here that we have the diameter listed as 250 millimeters, a 0.8 BAR with a hub ratio of 0.18. These will go right into PropCad in our principal data field. So let's do that right now. I'm going to start a new project. I'm not going to save that old design. And I'm going to enter just the basic information about the project. It's a KP505. It's from the Chryso propeller study. It's a 250 millimeter model. The regular propeller is 7.9 meters in diameter. And now I'm going to begin setting my data. It's a keyless shaft. It's 5 blades. It's 250 millimeters. And I'll just put in a sample client here just so that that information is displayed on the drawing. This is just the basic information. The diameter and pitch are on this main page in order to allow for easy rescaling. so that we could simply, if we were creating a variant later, we could just change the diameter to say 300 and regenerate the blade. Let's quickly go into our strength of materials and just define the material. We're not going to use classification societies in this demonstration, but for the estimate of weight, let's enter our material density as 8.3 grams per centimeter. And let's enter in a design power and RPM as well, so that information will be displayed on the drawing. Now we can progress to the blade definition. We will open up the section windows first. You'll see an empty table because we haven't created any sections yet. To generate the sections, we use the builder, which is essentially a parametric design wizard. We are going to use the builder to get our design about 80% of the way there. We know the sections are based on NACA 66 foils. We can see that again in the drawing, the block of the drawing, it will say section NACA 66 down here. We don't have a NACA 66 section in PropCad, so for now we're going to approximate our design using B-series sections, and we'll later refine the sections down. The pitch distribution in the design, if I quickly pull this up, we can see it's not a fixed pitch distribution, but that it's actually unloaded slightly at the tip and the root. This is very similar to PropCad's high thrust distribution, so we'll use that as our starting point. Blade outline, it can be difficult to quantify. In this case, we'll just use a B-series outline to get us something there, and then we'll manually enter our chord and skew positions to refine the blade shape into the correct outline that we want. So for now, I'll just select B-series, and I'll enter the expanded area ratio that I know from the drawing, the 0.8 BAR. Let's progress down to the skew distribution. This is a B-series style skew distribution, but actually it's quite heavy on the trailing edge side, and there's less skew angle on the leading edge. So let's just start with a cubic for now to approximate that. The cubic will actually have no skew angle on the leading edge, but we can refine that later. Expanded skew at tip is actually a value that we'll need to calculate. What we'll need to do is we'll need to measure the skew angle at the tip, and then we'll need to calculate the expanded distance. The distance, the tip foil is skewed in the expanded view. We divide that value by diameter to get a non-dimensional value for skew at the tip, which will scale with the propeller diameter. So if I go to my drawing here, what I can do is I can measure this point here and get a skew angle. I've done this already, and I've pulled most of the information out of the drawing that we'll need for this project. So I can see that at the tip of the propeller, the R/R of 1, the skew angle is 24.18 degrees. From there, I can calculate the expanded skew. This is a pretty easy calculation to do. It involves the pitch and some of the other geometric properties, but you can calculate an expanded skew here, and then you can calculate a tip skew by dividing the expanded skew by the diameter of the propeller. So you'll see the formula for this field here is just the expanded skew at the tip divided by the diameter, and we get 21.830. So let's enter that here into our expanded skew value, 0.21830. Again, from the drawing, we can see that the hub ratio is 0.18. So we're going to enter that in here as well. There's no shaft in the drawing, so let's just assume it's a 24mm shaft with a 1 to 10 taper, very typical of metric propellers, and we'll enter 51mm, which is the length of the hub on the drawing itself. Progressing into thickness, we can use a user-defined thickness to allow us to define the values at the tip and the root. Another option might be to just assume that it's similar to a B-series, but since we actually have some thickness values, let's just enter them. If we go to our distributions here, we can see that our thickness at the tip is 0.923, and at the 0.25 is 10.178. So let's enter those values now. 0.923, and 10.18. That'll be good enough for now for this first cut, because we're going to refine this later. The other thing I'd like to point out is this thickness distribution here is not quite a fully linear. It's what we refer to as a cantilever, where it's actually thicker at the root than it is at the tip, and it changes non-linearly. So we'll select a cantilever thickness distribution to get us as close to that distribution as we can. So I'll select cantilever there. For now, we will ignore camber and cup, but this propeller does have some camber in it, so one way to approximate the foils may be to use a standard B-series and then add some camber in. We're actually going to use the foil offsets themselves later, so for now we'll just use this as our first approximation. We'll click build here. The sections data is now populated with distributions. We can look at any one of these sections here and pull up the offsets that have been generated by PropCad. Everything appears to be going well so far, so let's hit OK and take a look at our design. It's starting to look like the propeller, especially if we look at the aft view here. We can see that the blade shape is starting to be very similar. Let's pull up the drawing now and see how we're looking. I'm going to fill in all the options just to get a default drawing on the screen here. Here we go. And we can see in our profile view here that our thickness distribution is looking good. Our pitch distribution is a little more unloaded in the root than it is in the drawing here. And our expanded view looks good, but the outline is not quite right. We can see that this is pretty much a straight edge here. And if we look at the view here, this is not straight at all. So we know that we have some tweaking to do. A lot of this is due to our simplified skew distribution. We can see the cubic here, it goes up and then to the left. There's no positive skew angle on the leading edge. That we know that we actually do have positive skew here. So what are we going to do about this? Well, basically, we're going to manually edit the section data. The first thing we have to do is extract the section data from the drawing. This can be manually measured. Oftentimes, there's a table provided with a propeller drawing that includes the distributions. Many times, they can just be pulled directly from the drawing. And that's what I've done here. I pulled these distributions at the top here from the drawing, and then I calculated the dimensional values of them. And the first thing we can see is that the R over R distribution is 1.95, 0.9, 0.8. It's actually pretty sparse at the tip for a round style propeller. If we compare that to what we have in our sections window here, we can see that we have a 9.875 and a 9.75. That's going to make it difficult for us to enter these distributions directly. So the first thing we're going to do is try and match our R over R position. Another quick thing I'd like to note is the last two radial positions are 0.25 and 0.18. Our distribution's in that 0.2, so we will have to spline in the extra sections and remove the ones we don't need. We're going to do that right now. First thing we're going to do is delete the 9.875 and the 9.75. Now we're going to spline in the 0.18 section in the root. I will enter 0.18 here. I'll use spline fit as my option, and I will select common as my offset density. That means that it will use the same chord-wise distribution of offsets that I used for the earlier sections. So I will hit insert here. This section gets added. I'll preview it. It looks pretty good to me, and I'll continue on. The next thing I'm going to do is I'm going to add a 0.25 section. And actually, if I click the section above I want to add, it will automatically populate that with 0.25. I'll select common again here. I'll use spline fit. I'll hit insert. I'll preview the section. It looks really good. So we are all set there. We have now matched our radial distribution. Oops, sorry, I actually have to delete this 0.2. Now we've matched our radial distribution. I'm just going to hit OK to accept, and I'm going to pull that back in here. Now what we have to do is we have to match chord, thickness, skew, and pitch in order to get the same distributions that were in our Creso drawing here. Oops, sorry about that. What I'm going to do is I've already put these in Excel. at the given R over R positions, and I'm just going to be able to copy and paste them from Excel. So I'll take the pitch over diameter ratios that I measured or was given from the drawing, the same values that are published right here, and I will take those, and now that my radial distribution matches, I'm just going to paste them in. And I'm going to go back in here, and I'm going to take the rest of the distributions. I'm going to take chord and thickness. I can do 2 columns at once. And again, I'm going to paste in chord and thickness. And I just want to check here to make sure there's no questions. Good audio. The last distribution here is rake. There's no rake in this propeller. Sorry, actually I missed skew. So let me put the skew distribution back in. Yes, I have 2 copies of my clipboard. Before I progress much farther, I've just been told maybe we lost some audio. Can everyone hear me okay? Is there any problems with the audio here? Oops. Okay, no problems. Great. Sorry about that. All right, let's continue on here. Someone just came in and asked me if the audio was working properly. They tried to sit in, and I guess we're having some issues, so it's probably just on their end here. So let's continue here. I pasted in skew, and I accidentally pasted that in the rake column, so let me just zero that column out here. All right, so now I pasted in chord, thickness, skew, and pitch. So I can hit OK to accept this. It's going to save the changes, and it's going to modify the design. If I refresh my drawing view here, and let me full size this, you should see the outline of the propeller change. And now we're getting even closer to our drawing here. If I can make this a little smaller, we can see them side by side. We can see that the expanded and projected views are very, very similar, and that the profile view also looks really good. But we actually can see that there's a few dimensions in the hub here that need to be fixed. So before we progress into the sections, and I closed that, but I wanted that. Let's edit the hub values. On the drawing, the forward hub diameter is 38.75. The mid hub diameter is 45, and the aft hub diameter is 38.75. I had that wrong. This one's actually 47.55. I apologize for that. We still have the same shaft diameter, and the axis location on the drawing is 28.5. So let's just put those corrections in, refresh here, and we should see the hub geometry change slightly. So now at this point, our propeller matches the blade shape of our original design very well. Our pitch distribution is matched, our thickness distribution, and the propeller outline itself are all matched. But we can see, if we look at the differences in the section shapes, and let me just pull the drawing back up. We pull these side by side here. These section shapes are definitely different than the section shapes we have in our drawing. And so what we're going to do is we're going to pull the offsets out from the publication, and we're going to enter those into PropCad in order to make our design a little, or to make our design fully match the final design. Here are the section shapes that are in there right now, and I just wanted to show you that. You can see it's this is the 0.7. It's a completely flat face, and the face is where the pitch equals 0 plane. If we look at the drawing here, we can immediately see, hopefully, that these are based off a nose-tail line, that they're not face stacked. So we know that we need to do some correcting already. That was just to convince you that we had to actually put these section shapes in. When you're pulling up section shapes, it's really helpful, I think, if you look at the help file here in PropCad and you look at the library propellers. You want to save yourself as much work as you can. And so if these sections can be easily represented by some of the library propellers, you can save yourself a lot of work by going to those sections. Now, unfortunately, the NACA sections, there's nothing in here that really represents those, and so we're going to have to enter those in manually. But in the future, I just wanted to point this out as a reference for people that if I'm recreating a propeller, one of the first things I do is determine whether I'm going to have to recreate the sections, and so I'm looking for a library propeller that has a similar shape that I can either use as a starting point, or I can modify manually, or I can just add camber to and get the desired shape I need. So one way to edit offsets would be to manually adjust the points in each section. That's very time consuming when you have a lot of sections, and also you can't reuse that data very easily. So what we want to do is we want to do something called a sections definition, which is basically a distribution of foil shapes that we're going to use that's going to get scaled to our chord and thickness in our builder. And let's go into the builder here, and let's set all our rest of our distributions to be locked. Now that we have everything entered the way we want, that nothing has changed, things rescaled when we use the builder again. So we're going to set these all to locked. And I'll hit OK to build the propeller. Again, none of our data should change. The chord zeroed out. That's OK. We'll hit OK. Nothing's changed here. And now we can go in and we can actually do an import here in order to import a sections definition. Now, what do I mean when I say sections definition? Let's go back to the data from the KP505. These are the distributions which describe the shape of the blade, but the shape of the foil shapes is typically given in a table of offsets, typically a 2D table of offsets. Here you can see the 2D table of offsets for the KP505. I've just gone and plotted these here for each section so you can kind of see the shapes. You'll notice that these are based off of a nose-tail line, so they go below the y=0 plane, which our B-series sections did not. And you can see that they're quite more or less symmetric in the very root, and they flatten out as the camber is added into the foil. So these sections are NACA 66 sections, which already have camber in them. So this way we can avoid using added camber in the builder. And what we'll basically do is we'll take the X and Y offsets here for each section, the face and the back, and we're going to format those into a format that PropCad can read, which is called a section definition, a .sect file. As you can see, these are the offsets, and we have individual control of each section shape for each radius, so you can have sections that change. You don't have to use the same foil for each one. Also, what's important about this section file is because we're using it here in PropCad for the sections and the radial distribution, this is going to become our resulting radial distribution. We have a 1, we have a 9.875, a 9.75, a 9.5, all the way down to a 2.5 and a 0.18. So what will happen in PropCad is our existing distributions that didn't have a 9.875 and a 9.75, those values will be splined in when we import this file here. So what I'm going to do is I'm going to click import, and I'm going to select my .sect file. The rest of these values are set to lock, and so we shouldn't see any change, although there seems to be something going on right there. The last two values of thickness were 0. I'm not sure why, but what I can do is I just copy it and move those down, and what I'll do is I'll fit these cells here so that it will be a nice smooth distribution, so that it will move cleanly from, yes, I need to make that smaller. Come on. And 0.1. Sorry about this. Just a quick little fix here to get these a little smoother. And now we can take a look at our R/R of 0.7. We can take a look at the section shape. We can see it's definitely different. It's not a y=0 shape anymore. It's a true nose-tail NACA 66 shape that has some camber in it. We can hit OK to accept this, and we can hit OK to accept our design here. So, whoops, Let's switch to the 3D view here. We can see our propeller is looking nice and smooth. We can preview all the data and make sure that the tip looks good. It's not too bad. It looks pretty good. The blade is actually on the hub here, and I think the hub data may have gotten reset on that build. So let's do 47 and 28.5. Let's refresh that. There we go. And now let's look back at our 3D view. We can refresh this. Now, one thing that becomes apparent here is that the profile view here actually looks a little different than the one that we had in the Creosote. But actually, this one is a simplified view because we can see these sections are stacked about the nose tail line. And so therefore, this thickness here should actually be on the backside of the maximum thickness line, just like it's showing up in PropCad here. So that's good to see. We've manually edited the data, and now we have our section shapes. This is more or less as close to the design as we are going to get. And from here, we would export the drawing into the 3D model. First, I'd turn on all these sections. One thing I like to do personally is actually take out some of the sections near the tip so that it's not so busy. I'll do that real quick. And then I could save this as a PDF and send to my client, or a DXF, depending on the format needed for the drawing. We have one here, so let me, is this the new one or the old one? That's the old one. Let's take a look at the new one here. And there is our new drawing in PDF format. The other thing we can do is we can export a 3D model of the propeller in a variety of formats. One thing we like to do is we like to talk with the CAD program itself and use the native surfacing tools in the program. So you'll see a lot of PropCad macros here. You'll see the Rhino macro and the SolidWorks macro here. Those will build the surfaces natively inside the CAD program. And we also have a few other point clouds and things like that. If we wanted to save these distributions for reuse in PropCad, we would just save the distributions, maybe make a new file, and we could save all the KP505 distributions for use in another project, maybe a derivative project or something like that. The last thing I wanted to show you is actually the propeller built in SolidWorks. So what I've done is I've recorded a video here, and hopefully this works. So this is the macro being executed in SolidWorks, and I apologize for the compression quality on the video, but you should be able to see everything. And I'm not doing this. This is just the macro running here, so you can see how the propeller is built. It'll basically export all the sections as curves, and the curves are being turned into lofted surfaces, which are being combined into a solid and then patterned around the hub. And this really is saves a lot of manual labor within a CAD tool, because propellers are not exactly an easy thing to model within any CAD tool, especially SolidWorks, which happens to be a solid modeler. So I just wanted to demonstrate quickly that the export abilities and how you might your design out of PropCad and into the manufacturing environment. Now we've gone through all the typical steps to recreate a propeller from a drawing specifically. I want to thank everyone who was able to join us for this PropCad webinar, and I also want to quickly address any questions that you guys may have. I didn't see any questions come through the text window, and so what I will do is I'm going to turn this to Q&A mode. Let me stop screen sharing here for a second. I'll turn this into Q&A mode, and you can unmute yourself or use the text chat window here in order to talk to me and ask some questions.
All attendees are muted and may unmute themselves by pressing *6.